Hello guys, and welcome back to, something, wait, hold on, I don't even know. It's been a while since I've played Minecraft. In my world it's been a while. It might have been like, actually no, YouTube time flows in the exact same rate as regular time. Okay, right, time is time. Alright, anyway, so today I'm going to do something rather enlightening, informative. I'm going to be doing some microprocessor design. So this is going to be some very simple microprocessor design, and what we're just going to be doing is designing addition and multiplication processing units. So this one will be for add. Alright. And then and then let's see, I gotta get this lined up because I'm that guy. Alright, and this one will be for multiply. Oops. Don't worry guys, I can spell sometimes. Alright, so there we go. Addition, multiplication. Whatever. Add, multiply. Same difference. Alright, so, oh, no, that's not where those need to be placed. And I'm going to be hoping to design some simple gates. Not gates. Circuits, that's what I'm looking for. Words, there's too many of them. Alright, I hope to be designing some simple circuits to do one little line of the calculation required to multiply and to add. So we're going to start out with addition, and how this is going to work is what we need is a line for each possible input or output. So, for example, we add the first bit. Alright, so let's say we're adding 1 plus 0, no little add-on things. Alright, 1 plus 0. So what we want is for this row to be off on top. Alright, so, oh, no. So how you design that is like this, and then this is something I like to call a carryover bridge. It's pretty much just a giant AND gate. Alright, so that's all off, which means the output is on. And the net output is on. Now, how you combine the gates, the AND gates up on top to form an output is very interesting, because what this over here is this is a carrying gate, or carrying input. It comes from the carrying gate set. So, let me just build a couple more of these gates so I can demonstrate that property. Alright, so I have finished a couple more AND gates, not many, just two, to demonstrate the first section. So this is the output, alright? So we'll just have, let's call it a redstone lamp, and that will be the output for now. And this is out. So, what this represents is every single possible combination that leads to 1 and only 1 as the output. So, we're not looking at 0, 1, and we're not looking at 1, 1, we're just looking at 1, 0 for the time being. Now, the next thing we want to do is we want to actually build the gate that represents carry. So for this gate, we're going to be carrying a 1. And we're also going to have a 1. So, as we all know, 1 plus 1 plus 1 is 3. And 3 in binary is represented as 1, 1. So, in order to do that, we want all of these gates to turn off, or all of these torches to turn off for the gate. Now, let's actually use a different block here to represent that we have entered the domain of multiple outputs. So, off at the end of this microprocessor circuit, we're going to have a carrying output, and that carrying output will lead into that input eventually. Now, the input's going to, once all the designing is done, be on the other side of the processing chip. So, now the string that we'll be able to perform is not only is that output on, but the carrying output is on. And the carrying output will talk to the next chip down the line and tell it that essentially this lever here is flipped into the on position. Now, all I have to do is finish up the 2-part adding, which means that carrying is on but output is off, because as we all know, 1 plus 1 is 2, and 2 is 0, 1 in binary. So, let me just do that. And that section is now finished. So, all I did was I put together a couple of these gates so that now every possible combination will yield the correct result. So, if we do 1, or 0 plus 1, that's 1. 1 plus 1 is 2. 1 plus 1 plus 1 is 3. Wait a second. Hold on. Something appears to not be functioning correctly. Did I forget a torch? No. No. Why are all these on? So, you shouldn't be on. Why are you on? You should be off. Oh, I forgot a piece of redstone. Oops. Alright. So, this part here is to keep the carrying output from interfering with the output. And that's what these repeaters are for, because there are certain cases in which both outputs need to be on, and there are certain cases in which only one of the outputs need to be on, and I want them on the same wire, so I do not want them interfering with each other. Alright, now, that is how that's designed. One thing I am going to quickly do is reverse all of the repeaters. And now, you can imagine that right here, we may have the stone input line of another set coming across and powering up that row. Alright? So, that is the addition component done. Now I'm going to do a little bit of futzing around and see if I can design a nice little multiplication circuit. Alright, so I've worked out how binary multiplication should look, which is like this, and then over here I have multiplication in decimal, and they actually both yield the same result, because this binary number is that in decimal. So now all I need to do is build something where if the digit is 1, it carries down, and if the digit is 0, it's set to 0. So what I'm going to have is a single bit at a time versus this whole string. Alright, so now I have made a single multiplication gate. Now, you might notice that these things look very different, but take up about the same amount of space. So this one, actually, this one's going to take up a little bit less space than this one. This one is 9 of those long. This one is only 8 long. And this one is 1, 2, 3, 4. Well, this one is 1, 2, 3, 4. Okay, so this one has slightly larger dimensions than that one, but this is a multiplication gate. So how this is going to work is for each input bit, there will be one of these circuits, and for the 8 bits, it will either have that on or off, and then it will have the exact same second input all the way across here for each bit. And then what will happen is, let's say that we're multiplying this number, whatever this number is, and we're multiplying it by 1. So that output would be chucked out to some cache, where it would be stored in the processor and then siphoned through a couple of, oh my god, an extreme number of specialized rapid-fire addition gates, and then a final 2-byte output. Or no, okay, there's so many bits in a byte. Yeah, so a final 2, or is it bytes in a bit? Hold on. It's gigabits per second is internet speed, but gigabytes is storage. Okay, so yeah. This is so many bits of input, and it will yield 2 bytes of output data, because you have to store it in 2 8-bit chunks. So if we look here, how many is that? That's 7. So that's 1 8-bit chunk, and I'm being called on Skype. Alright, sorry about that. So as you can see here, this is 1 byte of data, and this is a second, if I can highlight it, second byte of data. Now this isn't a full byte, but we could just slap a 0 on the front and it would be a full 8-bit byte. So you would, no, don't close that. And also, please don't lag. Alright, so anyway, it's going to take a lot of addition power and some handlers and a little bit of RAM, or just rapid access memory in general. And it's also going to take a bunch of these big 8-bit gates, or 8-bit circuits for multiplication, to get a whole multiplying set finished. However, I was rather surprised by the simplicity of the 8-bit multiplication single circuit. I thought it would be a lot more complex, but really its size stacks up quite nicely with the addition circuit. So, for next episode of this, I plan to tie these together and make addition, subtraction, multiplication, and maybe go for division. So, until then, see you next time.